All right, ladies and gentlemen, we are in our optics note packet on Refraction 101. So we finished up our information about reflection, and now we are talking about refraction, which will mean instead of about mirrors, we'll now be talking about lenses. So refraction is based on the idea that light is passing through one medium and into another medium. The ultimate question is really what happens. A good way to think about it is if you're running on the beach and you run into the water, what happens to your velocity of you running on the sand versus running into the water? The thought should be when you think about that is that you slow down. It changes your velocity, and also the same thing would happen as if you were running in the water and then you changed into to running on the sand. Again, it would change. So refraction fact number 1, as light goes from one medium to another, the velocity changes. That should be written in your Refraction 101 information. So suppose light comes from air, which in this case will be considered a vacuum as well, because its index of refraction is 1, and we'll get to that in just a minute. And it strikes a boundary at some angle of incidence measured from the normal line. Remember how we measure our angles? Always from the normal line. And this is like a plane mirror in the fact that the normal line is always going to be drawn perpendicular to the interface between the two mediums. And let's say it's going to go into water. So water is going to be medium 2 and the vacuum is going to be medium 1. The ratio of speeds can be compared by looking at the index of refraction. Okay, the formula for index of refraction is on your formula chart. Okay, it is listed as n equals c over v, where c is going to be the speed of light in a vacuum, which is given on our formula chart as 3 times 10 to the 8th meters per second. And then the speed of light in the medium is always going to be the lower one. Now notice the index of refraction is always going to be a what I call a unitless or naked number, because we're going to have meters per second divided by meters per second, which are going to cancel out. So the denominator in this case will always be smaller and produce a unitless value, like I said, that's greater than or equal to 1. This value is then called the new medium's index of refraction. So it's always really just a ratio of the speeds. That's what index of refraction is. And there are all substances have an index of refraction, and they can be used to identify the material. And also there's typically lots of different tables and things like that that you can use that will help you with that. Lots of times if you know the material, they'll give it to you. So suppose you decide to go spearfishing, and unfortunately you aren't having much luck catching any fish. The cause typically is due to the fact that light bends when it reaches a new medium. So the object is not really directly in a straight line path like you think it is, but rather its image appears that way. The actual object is on either side of the image you're actually seeing. So what happens is, believe it or not, you think you're seeing where the ghost fish of Nemo is here, but really Nemo is over here. Okay, he's a little bit lower. So when you are thinking about it that way, the light bends as it changes, as it comes out of the water into the air. So you have to think about the fact that you're going to actually have to aim a little bit closer to you when you're hunting for that fish. You can also do this with a penny in a cup, and you can put the coin so that you can't see it when there's nothing in the cup. So you can just look across the edge and you won't be able to see it. But then when you actually fill it with water and you look at it the same sight line, you'll be able to see it. And that's because of that repositioning or that bending of the light as from where you see it and from it changing mediums. So refraction fact number 2. as light goes from one medium to another, the path changes. So not only does its velocity change, but its path also changes. That needs to be written down as well. So what exactly is light doing when it reaches a new medium? We don't want you to think that all the light refracts. Some of it actually still reflects. So we have our normal, part of the incident ray comes in, strikes the surface, and then reflects off. And lots of times we see this in water, where we'll see reflections, but we can still see things underneath the water too. That's because some of the light is going to reflect off the boundary. Some of it is going to refract through the boundary, though. So the angle of incidence is always going to be equal to the angle of reflection. We learned that law in our reflection section. But the angle of incidence will be greater than or less than the angle of refraction, depending on the direction of the light, depending on whether it's going from a higher index of refraction to a lower index of refraction, or from a lower index to a higher. It does different things. And so we'll talk a little bit more about that. But those angles are not ever equal because of the fact the angle of incidence and the angle of refraction are not equal to each other. They're always going to be different from each other because of the bending of the light. So the index of refraction, N, for air or vacuum is equal to 1. The index of refraction for water is 1.33. If you're going from a low N to a high N, your speed decreases and the angle bends towards the normal. The thought is that when you have a higher index of refraction, that's going to make the light bend more. And so it's actually, the thought is when that number is higher, it's going to bend towards the normal, because as it goes into that new medium, it's going to slow down. And as it slows down, it can't be going at that direct angle anymore. So that angle has to go lower because of the fact that it's slowing down. Okay. Then the index of refraction for air is still 1, and the index of refraction for water is still 1.33. But if you're coming from the water and going into the air, your speed is actually going to increase. And when it increases, it's going to move away from the normal. So that angle is going to get bigger instead of getting smaller. If the angles are equal to each other, which it does happen sometimes, I said they wouldn't be equal, but sometimes they will, then what that has to mean is that the N of the two mediums is exactly the same. Okay, that's the only way the ray will pass straight through it. So really, when we think about the light coming through the window, it actually refracts from the air as it comes into the window, and then as it comes from the window back into the air of my classroom, it refracts again. So every time it reaches a interface between two mediums, or a boundary between two mediums, it's going to refract if the index of refractions are different. So now we could be in that index of refraction and or that Snell's law square. You could have put everything I just said in that index of refraction square. But a scientist by the name of Snell discovered that the ratios of indexes and the ratios of the sines of angles are the same value. So he was able to do the index of refraction ratio over equal to the angle ratio, which then actually, and it was the inverse of the angles. So the index of refraction for 1 over the index of refraction for 2 would equal the sine of the theta 2 over the sine theta 1. That's actually Snell's law, and that's on your formula chart as well. So when we cross multiply, all the 1's are together on one side and all the 2's are together on the other. So that I'm talking about the angle here and the index of refraction here, and the angle here for the air and the index of refraction here. So I have an example problem, and this is actually in your notes as well. Okay, the refractive index of the gemstone Aquamarine is 1.577. Suppose a ray of light strikes a horizontal boundary, which again is that interface of the gemstone, at an angle of incidence that's 23 degrees from the air. I recommend drawing the picture. Lots of times seeing it helps you. So this angle of incidence right here is 23 degrees. We know that the index of refraction for air is 1. You need to know that, by the way. That's something I do expect you to know. Then we were told the index of refraction for aquamarine was 1.577. So I want you to calculate the speed of light in the aquamarine. Well, if you remember, the speed of light can be figured out by looking at the index of refraction formula. We know that N equals C over V. So we could find V by rearranging that formula and using the speed of light in a vacuum, which we know is 3 times 10 to the 8th, divided by the index of refraction for the aquamarine, which is 1.577. So we can come up with a velocity of, and hopefully you do that in your calculator, but if not, you can check it. And this would be 1.9 times 10 to the 8th meters per second. Okay, so then the second question that I want to ask is, what is the angle of refraction within the aquamarine? So now I'm trying to find this particular value right here. And so now I'll use Snell's law to do that, because then I can do N1 sine theta 1 equals N2 sine theta 2. Well, I know my water is 1, or my air is 1, and that angle is 23 degrees. And then I know my N2 is 1.577, and I'm looking for this theta 2. So then I will do my manipulation, take the sine of 23 divided by 1.577, and then do the inverse trig function to find the theta itself, and I should come up with 14.34 degrees. Okay, we'll do quite a few problems like this. Okay, so hopefully these two formulas are making sense off of what we've already done in our packets. Okay. So there is a special situation that's called total internal reflection, and this is a special type of refraction that can occur only when traveling from a high index of refraction to a low index of refraction. It's really important that you remember that. It can only happen then. So only if I'm coming from the water and trying to go into the air. So there's a certain angle that my angle of incidence right here can be, which will cause this to be a 90-degree angle. Okay? And so we call this angle, when that's the case, to be the critical angle. And so we can change up Snell's law a little bit so that it keeps it right on that area and it'll keep it there. If we go anything higher than the critical angle, so we keep moving it further out, making it larger, then it'll actually reflect back into the material instead of leaving the boundary at all. So if we exceed the critical angle for the material, then the ray will reflect back internally, which, because of that, we call it total internal reflection. Believe it or not, fiber optics and things like that work on this concept. Also, the way that diamonds are cut work on this concept, because they want the light to bounce around inside of your diamond before it comes out multiple times, because every time it bounces around inside there, it splits up a little bit more in the coloring, so that when it finally does find the surface where it can exit, then it's actually more brilliant. So that's one of those quality things that you look at. And in your notes, this is under the TIR section, by the way. So, yeah. So right here, I've now exceeded this critical angle, so the ray is going to come back into the boundary, or come back into the substance. So the question is how can we really calculate the critical angle? Well, remember that refracted ray has to equal 90 degrees. So we can still use Snell's law, but we can make that 90-degree sine just a 1 value. And if we do that right here, because we would substitute it in right there, then we've now got this formula that really is our critical angle. The sine of our critical angle is the ratio of our index of refractions of our faster medium, or our lower, to our higher. Okay, ratio. So, suppose a ray of light is traveling in heavy flint glass, which we know the index of refraction for it's 1.65, and once it strikes the boundary, it enters air. Calculate the critical angle for that flint glass. So again, I gave you this particular picture. I recommend putting it in the example in your notes as well. So we want that refracted angle to be 90 degrees if we want to find a critical angle for our eye. So we're going to use sine over Snell's law, and sine theta for our critical angle equals n2 sine theta 2, and we know that sine theta 2 should be 1 because of the fact that theta 2 is going to be a 90-degree angle. So we're going to do 1, which is our index of refraction for air, divided by our flint glass, and then we're going to do our inverse trig function, which should come up with 37.3 degrees. Okay? Hopefully you guys understand what we're talking about so far, and if you have any questions, bring them to class and we will talk about them then. I'm going to stop there with this recording, and we will do types of lenses and ray diagrams in class.